Hello guys, my name is Aditya Singh and I am from MTech IT 5th Sem, and today we will discuss about the End-Sem solutions of data science. So the first question we have is hypothesis versus data driven. Distinguish between hypothesis driven and data driven paradigms in data science. Provide an example of each. Hypothesis driven paradigm starts from a clear hypothesis based on domain knowledge or theory. Example of hypothesis H1, giving 10% discount increases average sales by at least 5%. Workflow. Step 1, formulate null hypothesis HO and alternative hypothesis H1. Discount has no effect on sales. H1 discount increases sales. Design Step 2 is design experiments. Group A no discount, group B 10% discount. Step 3, collect sample data, daily sales from both groups. Step 4, apply statistical test. Step 5, compute p value and compare with significance level. Exa- uh, Example 0.05. If p value is less than alpha, then reject H0, accept H1. Important data is collected and analyzed with the primary goal of testing a specific hypothesis. A hospital hypothesis that a new drug reduces average blood pressure by 10 mmHg. They collect before after data on patients and use hypothesis testing to verify. Next is data driven paradigm. Starts from large amounts of data, often without a stronger prior hypothesis. Goal: the data speak and automatically discover patterns, correlations, clusters, rules. Typical workflow: Step 1, collect raw data. Step 2, exploratory data analysis. Visualizations, histograms, scatter plots, correlation metrics, compute summary statistics, mean, median, variance, etc. Step 3, train ML models. Step 4, interpret output and form new hypothesis. Step 5, input millions, for example, input millions of transactions from a supermarket. Each transaction is a set of items: milk, bread, eggs, etc. No prior hypothesis was formed, patterns emerged from data itself. These rules can later lead to business hypotheses like customers who buy smartphones are likely to buy accessories. Key distinctions: hypothesis driven theory is hypothesis, data is test. The second part of the question number one is differentiate between structured, unstructured, quantitative, and categorical data with suitable real world examples. Structured data. Data organized in fixed rows and columns with a well defined schema can be stored in relational databases. Easy to query using select, where, group, by, etc. Example student table. Characteristics: each column has a specific data. Constraints can be enforced. Good for OLTP systems, classical reporting. Unstructured data. No predefined schema or fixed table format. Text media or documents where structure is irregular or implicit. Examples are email, PDFs, work documents, images, audio files, video files, etc. Social media posts, comments, reviews, etc. Storage, file systems, no SQL databases. Challenge: need NLP, computer vision, or similar techniques to convert into useful features. Then we have got quantitative data. Represents measurable quantities, numbers on which arithmetic operations are meaningful. Two types. Continuous can any take any value in an interval. Examples height, weight, temperature, etc. Discrete take integer counts. Example number of counts in students in class, number of transactions. Real world example are monthly salary of employees in rupees, daily sales in units. And categorical data represents labels or categories rather than numeric magnitude. Arithmetic operations do not make sense on labels. Types nominal, ordinal. Real world example are product category, loan status, relationship status. Structured data may contain both quantitative and categorical columns. Unstructured data is often converted into structured form using feature extraction. The question number 2 is first part we have got base based decision algorithm. So the first part is write an algorithm that uses Bayes theorem for decision making. Bayes theorem P a probability of H with respect to E is equal to probability of E respect to H into probability of H upon probability of E, where H is hypothesis, E is evidence, P of H is prior probability of hypothesis, and P of probability of uh, E with respect to H is likelihood of observing evidence when H is true. Probability and P of probability of H with respect to E is posterior probability. Input training dataset D with records. Each X is equal to X1, X2, Xd is a feature vector. Assumption: features are conditionally independent given the class. Training phase: for each class CK, estimate prior. For each feature xj and class ck, estimate likelihood from training data. For categorical xj, use frequency with Laplace smoothing, where v is equal to number of possible categories of xj. For continuous xj, assume xj and estimate from samples. Prediction phase: decision making using Bayes. Given new instance x is equal to x1 dash dash dash. For each class ck, compute unnormalized posterior score. Choose class with maximum posterior. Output y as decision. The algorithm directly applies Bayes theorem for classification decisions. Goal of association rule mining: discover rules of the form x to y, where x and y are item sets and x intersection y is null. Supports x to y. Support is equal to support x union y. Confidence x to y is equal to support x union y upon support x. Input transaction database T. Each transaction T is a set of items. Minimum support threshold minisub. Minimum confidence threshold min confidence. Output: all association rules x to y with support is greater than minimum support and confidence is greater than minimum confident. Algorithm: a priori algorithm. Frequent item set generation part 1. Scan T to find all one item sets with support is greater than minimum support is L1. For k is equal to 2 to generate candidate k items ck using lk minus 1. For each transaction T in T, increment count of all candidates in ck that are contained in T from lk is equal to support is greater than or equal to min support. Stop when lk is empty. Association rule generation from frequent item sets. For each frequent item set f in UK LK with f is greater than 2, for each non-empty proper subset A of f, let B is equal to f minus A. Compute confidence. Confidence A to B is equal to support f upon support A. If confidence A to B is greater than minimum confidence, output rule is A to B. Example: frequent item set f is equal to milk, bread, butter, etc. Support is equal to 0.2, that is 20%. Subset A, milk, bread, support A is equal to 0.25, that is 25%. Confidence 0.2 upon 0.25 is equal to 0.8, that is 80%. If minimum support is less than 20% and minimum confidence is less than or equal to 80%, rule is printed. Pseudocode summary: generate all frequent items using a priori For each frequent item set f for each non-empty subset A of f, b is equal to f minus a. If support f is upon support A is greater than or equal to minimum confidence, print rule A to B with support. So question number 3 is compute mean, median, mode and standard deviation for a given small data set. Explain when each measure is appropriate. Consider data set X with n is equal to 8 values. X is equal to 2, 4, 4, 4, 5, 5, 7, 9. Formula mu is equal to 1 by n and summation of xi. Compute summation of xi 2 plus 4 plus 4 plus 4 plus 5 plus 5 plus 7 plus 9 is equal to 40 and n is equal to 8. So the mu will be 40 upon it, that is 5. So we have got the mean. Now we will calculate the median. For even n, median is equal to average of n by 2th and n by 2 plus 1th values. Here n by 2 is equal to 4, so take 4th and 5th values 4 and 5. Median is equal to 4 plus 5 by 2, that is 4.5. So the median will be 4.5. Third is we have to solve for mode frequency. So the mode is most frequent value. Frequency 2 is repeated 1 time, 4 3 times, 5 2 times, 7 for once and 9 also for once. So the mode will be 4, that is appeared for the most number of times. The next is standard deviation. So the formula is square root of 1 by n and summation of x minus mu ka whole square. We have mu is equal to 5. Compute square deviations. Sum of then we will take the sum of square deviations, that will be 32, and so the variance is 32 by 8 is equal to 4. So the standard deviation will be the under root of variance, that is under root of 4, and we will get a standard deviation is equal to 2 when each measure is appropriate. Mean use when data is roughly symmetric without extreme outliers, sensitive to outliers. Median preferred when distribution is skewed or has outliers, robust to extreme values. Example, median income of population. Mode best for categorical data. For numeric data, useful if distribution is multimodal. Standard deviation describes typical deviation from mean, used with mean in normal distribution. About 68% values lie within plus 1 sigma of mean. So the second part of question number 3 is what is the difference between errors and artifacts in data cleaning? Explain any two imputation techniques. Error in data. Data values that are incorrect relative to the real world value causes human entity mistakes, faulty sensors, transmission noise, misalignment of columns, unit mistakes. Example, age is equal to 250 years, salary is equal to minus 1000, date of birth greater than current date. Artifacts in data. Patterns or anomalies introduced by the measurement process, device or pre-processing, not by real phenomenon. Examples are sudden spike in ECG signal during electrode adjustment, duplicate log entries created by retry mechanism, step-like jumps in sensor reading when it is recalibrated. In analysis, artifacts may look like real signals and must be detected and removed. Data cleaning aims to detect and connect both errors and artifacts. Imputation techniques. Handling missing values. Mean median imputation for numerical data. Idea. Replace missing value with central tendency or that attribute. Mean imputation. Sensitive to outliers, best for roughly symmetric distributions. Median imputation. X missing is equal to median of observed values. Robust to outliers, best for skewed data. Mode imputation. Replace missing category with the most frequent category. Example city, Indore, Indore, Bhopal, Indore. So the mode will be Indore. Advanced techniques. KNN imputation. Find k nearest neighbors based on other attributes and use their average or majority. Regression imputation. Train regression model to predict missing variable using other variables. So the question number 4 is explain any 4 common feature engineering techniques for continuous or categorical data. First is one hot encoding. Categorical to numeric. For a categorical variable with m categories, create m binary features. Example feature city Bhopal, Indore, Delhi. One hot representation Indore 100, Bhopal 010, Delhi 001 avoids giving an artificial order to categories. Second is label encoding. Map each category to an integer label. Indore 0, Bhopal 1, Delhi 2. Useful for tree based models which do not assume linear relationship in label space. Caution. For linear models, this may introduce fake ordinal relation. Third is normalization. For continuous features, scales data to 0 to 1. Formula for a feature x. Example x min is equal to 20, x max is equal to 80 and x is equal to 50. Important for distance based models, KNN K means. The next is standardization. Transform feature to mean 0 and standard deviation 1, where mu is equal to mean and sigma is equal to standard of that feature. Useful for algorithms that assume normalized data. The fifth is binning or discretization. Convert continuous variable into categorical intervals. Helps models that work better with categories and can capture non-linear relationships. Sixth is polynomial and interaction features. Add non-linear transformations and interactions. Example, house price depends on area and number of rooms. Add feature A into R to capture interaction. The second part of the fourth question is what is sampling from a distribution? Describe inverse transform sampling or Monte Carlo sampling with an example. Sampling from a distribution. Goal. Generate random samples x that follow a desired probability distribution p of x. Example distributions uniform, normal, exponential, etc. Used for simulation. Approximating integrals, expectations, generating synthetic data, inverse transform sampling. Let target distribution have CDF. Generate U from uniform. Set x is equal to f inverse U. Then x has distribution f. Example, exponential distribution with rate lambda is greater than 0. Derivation for exponential using inverse transform. Start with CDF. Let U be uniform. Set U is equal to fx. Solve for x. Since 1 minus u is uniform on 0 to 1, we often use x is equal to 1 minus 1 upon lambda. Because u and 1 minus u have same distribution. Monte Carlo idea. Use random samples to approximate expectations. Example, estimate pi by sampling points in square 0 to 1 into 0 to 1 and counting fraction.